Hello, everybody. My name is Radu Lupoaie. I'm working for Keysight Technologies, and today I'm going to deliver a presentation, which is organized by Keysight Technologies Romania. A bit of history. So, who is Keysight? Keysight is a leading technology company with a short history of about 80 years. In which we have helped enterprises, service providers, and governments to connect and secure the world. We have products that help customers bring the solutions to market much faster. And we help them from design to prototype validation, all the way to manufacturing and to optimization after a product has been deployed in the live network, so to say. Who is exactly Keysight? Well, I mentioned 8 years of history. It all started with Bill Hewlett and Dave Packard in a garage in California, in what today we know as the Silicon Valley. They have been working on creating test and measurement equipment, and in 1999, the division that was making test and measurement equipment was spun off, and it became Agilent Technologies. And Agilent Technologies in 2014 split again, and electronic test and measurement equipment became Keysight Technologies. Agilent has a different path. And what happened? How did Ixia come into the picture? Ixia has also quite some history behind. It used to be Genova. Then it became Ixia from 2004 to 2017. And Keysight acquired Ixia in 2017 in order to enhance its portfolio and to cover all the layers of the tests, from the physical link all the way up to the application layer. So L1 to L7 on the OC stack was covered by having Ixia in the portfolio. In which industries do we operate? Well, we can say that it's all the industry sectors: wireless, automotive, energy, Internet of Things, aerospace and defense, and of course, networking and cloud. And at the core of our solutions are, of course, the engineers who some of them are best in what they do in terms of hardware, some others in software, in C++, C, in Python, RESTful APIs, and so on and so forth. What makes our engineers happy and willing to work with Keysight? Well, there are 4 main aspects. One of them is the fact that they work on the latest technologies, probably far earlier than other people in the market, because Keysight works on the technologies before they are even heard of by other people. We have an environment in which the employees grow and work autonomously over time. We work in a respectful, open, and diverse space. And last but not least, we think that success is driven not only by the technologies and the work, but also by having balance, work and life, and being motivated to do what we are doing every day. So in general, the key point would be that one key special ingredient in our solutions are the people. And we have visionary engineers who like and want to achieve breakthrough contributions to technology, and we offer them a great mix of benefits, because working for Keysight is probably like working for the best company in the world. No pun intended. So if you want to talk more, please visit our Keysight jobs website. Jumping into today's technical topic, as I mentioned, I'm Radu. I'm a technical consultant for automotive wireless solutions with Keysight. I have a very long title for my presentation, but I'm going to try to make the content crisp and sound. So we are going to talk about Cellular V2X and beyond, and how to turn impossible into reality when it comes to car-to-car communications. I'm going to start by presenting you Mike. Any resemblance to real people is purely coincidental. Who is Mike? He's an engineer working in the automotive industry, bringing innovation to it. And now he has a new wireless communication project to work on. And this brings him several challenges to overcome, such as is the RF performance good enough on his device? Is the throughput good? What about the latency end-to-end on his applications? How is the GNSS precision? So yeah, quite some challenges. In order to help Mike, I'm structuring the presentation today in 4 big chapters. First, we should talk why is it important to have connectivity in automotive. Then we will talk about C-V2X and its journey from basic to advanced use cases by using 5G and R. In the end, I will present you briefly the Keysight test solution for Cellular V2X, and then we can have some Q&A. Diving into chapter 1, connectivity matters now more than ever. Where is connectivity? Well, connectivity is at the center of the technology stack in automotive, because if we look at a car, what is it a car? It's a bunch of mechanical components, some sensors, nowadays more and more computing, an operating system, and software. So we are talking now about the software-defined car, features that are being enabled via software downloads, software upgrades, and so on and so forth. So how are all these done? Via connection with the outside world. So cellular connectivity, device-to-device type of connectivity, satellite communications allow the cars to communicate with edge computing hosts, with an automotive OEM backend cloud, or with the internet. And why is this done? Well, because we want to offer to the drivers and to the passengers telematics and mobility services, infotainment, and maintenance. As I mentioned, the connectivity is at the center of the stack, and by being there, it enhances safety, it provides sustainable transportation, and it also allows to have value-added applications and services for different companies in order to increase their revenue streams. So talking about the cellular connectivity in general and how it reaches the cars, of course, it all started with 2G some decades ago. It was that thing that was giving us voice on a bulky phone. Then we moved to 3G with circuit switch voice and packet switch data. The data rates were not particularly high. And then technology evolved towards 4G, which was all packet switched for voice and data. Latency throughputs were good, but they could have been better. And what happened? Well, industry and academia have worked and brought to humanity 5G. 5G on the radio side, also the core network, is developed with several use cases in mind. One of them is how to cater for massive machine type communication, so for Internet of Things, how to connect millions of devices. Then enhanced mobility broadband. This is a continuation of what we have seen in 4G, having high throughput on your phone, being able to watch movies, maybe to play some games. It's generally around high throughput. And last but not least, 5G also brings technologies around the self-driving car for mission-critical applications, where the idea is to have ultra-reliable link and very low latency communications. So it's not only 2G, 3G, 4G, and 5G, it's also the ITS, Intelligent Transportation Systems, and V2X, Vehicle to Everything Technologies, because it's has to do with automotive. Then we also have to consider that we need policy, we need regulations. So the European Commission in Europe, or the FCC in the US, the US Department of Transportation, these are the institutions that need to create the legal framework in which V2X would operate. Then in order to have V2X and intelligent transportation systems, deployed on a broader scale, we need to have standardizations and certifications. So here we have bodies such as 3GPP, IEEE, ETSI, OmniAir, GCF, and you name it. And last but not least, even if we talk about legal, even if we talk about certifications, we also need to have the industry that puts the engineers to work to make these things work. And in here we have 5GA. It's a 5G Automotive Association. It's a big organization comprising more than 130 companies from both the automotive market, so OEMs, tier 1 suppliers, as well as mobile network operators, chipset vendors, and all these companies are working together trying to create an environment in which C-V2X or V2X type of communications would be deployed. And another organization would be the European Automobile Manufacturers Association, which is only covering automotive OEMs. So the idea would be that we have basic safety scenarios, we would have advanced use cases for car-to-car communications, and C-V2X you will see in the upcoming chapters that evolves to 5G, because 5G offers a scalable radio interface, low latency communications, much higher throughput by operating in a wider spectrum of frequency, and C-V2X also evolves from broadcast types transmissions to unicast and multicast. So probably Mike is already excited and looking forward to the next chapter. So let's dive into chapter 2, the journey to basic safety use cases. So if we want to implement safety applications in the automotive world, we have, of course, two options. We can go wired, we can connect the cars, but this doesn't look extremely scalable, or we can do it wireless. So how do we do it wirelessly? Well, we have V2X. Basically, the communications happen between car and their environment. It can be car to pedestrian, car to roadside infrastructure like traffic lights or signs. It can be between different types of cars. It doesn't have to be a car. It can be motorcycles, trucks. And there is not only car to pedestrian, it's also car to network. So X can be anything on which you can put something that communicates. Why is V2X needed? Well, in the context of ADAS, of advanced driver assistance systems, which use ML in order to understand in which environment the car operates, and the data that it uses to crunch in order to understand where it is comes from different sensors: camera, radar, LiDAR, ultrasonic, HD maps, GNSS, so positioning systems. And V2X is not coming to replace any of them. It complements what is existing already in the automotive world. Some use cases enabled by V2X, you can think of some that are proposed by the SAE. It's the Society of Automotive Engineers. And one use case for C-V2X would be the emergency electronic brake lights. So imagine in this picture that the RV is the remote vehicle, has to brake for whatever reason, it needs to brake suddenly, and then it transmits a message over the air, it broadcasts a message saying, I'm braking very hard. And the host vehicle is another car that is equipped with C-V2X types of communications. And once receiving this message, the host vehicle can brake, and there won't be a sandwich accident here, so to say. Another use case would be the intersection movement assist. Again, here the host vehicle tries to enter this intersection. RV2, remote vehicle 2, is, let's say, parked here. The visibility is not great. RV1 comes quickly towards the intersection, but it transmits messages saying, oh, I'm going in this direction with that speed. The host vehicle would receive the messages and would understand that probably driving into the intersection would not be the best idea. So I mentioned a couple of slides before that the intelligent transportation systems are driven also by the legal framework in which they operate, by policy, and part of the policy is covering the frequency in which the technology is deployed. And around the world, in most of the countries, the 5.9 gigahertz band has some spectrum allocated for car-to-car types of communications. The technology that is deployed in this frequency is not harmonized across the globe. So currently in Europe, there are two types of connectivity methods that are used. One of them is called ITSG5, the other one is called LTE-V2X. In the US, it's also a mix, but the US has decided that LTE-V2X is going to be the de facto technology going forward, and DSRC will be slowly pushed out. And in China, for example, they have been going directly for LTE-V2X. Other regions, other similar discussions on how things are going to be. So V2X, how does it work? I mentioned that there are different technologies. Basically, the technology that was the incumbent used to be DSRC. It is based on Wi-Fi, on IEEE 802.11p, and it started in the beginning of 2000s, 2000 and so or so, to be deployed. With this picture, it may look a bit overwhelming, but what I want to point out is that if initially most of the lower layers of the physical link were covered by IEEE, then going forward, this tends to be skipped and the market moves towards the 3GPP defined technology, which is called Cellular V2X. So this is why I try to, in the first slides, I try to use the word V2X because V2X can be either 802.11p V2X or 3GPP based V2X, which is Cellular V2X. But going forward, I'm going to talk mainly about Cellular V2X, which is defined in the standards by 3GPP. How did 3GPP evolve this technology? Well, it started with release 14 to this would be maybe 3-4 years ago. Just to give an idea, release 17 was closed last year in summer. So release 14 was the first to define Cellular V2X. It was based on 4G LTE. And it was mainly defined for basic safety applications, cars that are broadcasting messages. Release 15 didn't bring a lot of changes. It was just maybe increasing the modulation scheme. So we have, in the end, more data that can be transmitted over the channel. It added transmit diversity, but the main concepts remain the same, and it still stayed a broadcast type of system. And release 16, I'm sorry, so last year it was release 16 that was closed in summer, and release 16 defines 5G V2X, which thinks about new use cases. It's not only this basic safety applications, the cars telling each other, hey, I'm here, be careful. Release 16 has been designed with the idea in mind that vehicle platooning can be enabled via 5G V2X, advanced driving, extended sensor, remote driving. I'm going to explain these a bit later. And what is new about it is that unicast and multicast transmissions are also possible. And in general, what 3GPP is helpful with is that it provides to some extent backward compatibility between the different standards. So yes, Mike is right. He should be keeping up with the standards because they are evolving quickly. It's approximately every year one new standard. Of course, the market has some latency in adopting them, but still knowing what comes out there is important. So let's dive a bit more into Cellular V2X. It offers two ways of communication. One of them in which the communication is done via the network. So car 1 here would be sending messages to the network, and maybe then car 2 communicates also separately with the network, and there is always this arbiter between the two nodes. The other type of communication is the direct type of communication. Basically, UE1, car 1 here, the truck, and the limousine are speaking, so to say, directly to each other. As you can imagine, network type of communication allows for longer ranges. Direct would refer to lower short range type of communications. When the cars are communicating with each other directly, they also need some synchronization. There is no E node B, there is no network that arbiters which node uses which resources at which time. So the technology has been designed to have some sort of synchronization. So in general, when there is car-to-car type of communication, the synchronization is based on the clock from the positioning system, GNSS. So it can be GPS, GLONASS, Galileo, whatever. And when the E node B would be available, then the synchronization is given by the time from the node, from the cell tower. In general, based on what is called as 3GPP and as Cellular V2X in the standards, the direct mode of communication has been the one that is mostly deployed. It doesn't require too much work from the operator. It actually requires zero work from the operator. And there are some operators doing studies and thinking how they can deploy this, but until some clearer use cases and probably billing modes are defined, I personally have the feeling that the network is less involved into Cellular V2X and is mainly the direct type of communication over PC5. So this is why I'm going to talk more about the direct type of communication, car to car. And how does it work? Well, you can think a bit, there is a lot of text on this slide, but think of it a bit like Wi-Fi. Basically, a car that wants to transmit a message would sense the channel on which it tries to transmit. It senses it for a certain amount of time, generally 1 second, in slots that are one millisecond long. Then it assesses which resources seem to be empty or less used by other cars, and on the resources that seem to be less used, it is going to make the transmissions of the data that it needs to send. So it's similar to carrier sensing in Wi-Fi to some extent. How are the resources defined for Cellular V2X? Well, in general, I mentioned in 5.9 gigahertz, the authorities, the legal, the government, or some authority that is responsible for licensing spectrum to different technologies in a country can offer either 10 or 20 megahertz for Cellular V2X. And then these 10, 20 megahertz are defined into 5 or more subchannels that are non-overlapping. And on these subchannels, then the transmissions can be made. As I mentioned, the time granularity for the messages that are being transmitted is 1 millisecond, and all the cars know when the boundary of this 1 millisecond is in a certain region by being connected and knowing the time from the satellite, from the positioning system. Which are the main KPIs that we look at when we have to test Cellular V2X? Well, of course, you can imagine that latency is of paramount importance. Then reliability. We need to make sure that messages that are relevant are reliably transmitted. So messages maybe at least from the cars that are close by. Then the data rate, how much can the channel absorb and transmit reliably. Then the range of the communication, depending if we are traveling at high speeds or low speeds. Of course, the range in which the communication system operates or is able to transmit reliably is becoming more and more important. So let's talk a bit more about how 5G comes into picture. And I would like to talk about the use cases. In 5G, it's not only these basic safety applications that are catered for. It's not only a car approaching an intersection and transmitting messages, I'm going in this direction at that speed, beware. But with 5G, the standards are thinking about use cases such as cooperative driving. You can think about here like vehicle platooning, and they consider that the link should be reliable enough to transmit payloads of 6,000 bytes 50 times per second, and the end-to-end latency at application layer should be roughly 20 milliseconds. Of course, this relies on groupcast and unicast transmissions. The idea would be that the car in front transmits messages, and the cars behind are able to maintain the speed and constant distance, and the distance should also be generally small between these cars and would be driving together in the same direction. Another type of use case is advanced driving. Of course, here we are talking about sharing sensors, sensor data, sharing some video. So imagine here cars approaching an intersection. One car wants to change lane. If they are able to communicate a lot more to communicate the intention, to communicate that maybe this car sees that there is a car approaching this intersection, it could send this information to the other cars, and maybe if this is an area with high-speed driving, it can become a lot more. It can become safer for everybody if they know which car goes where and what it senses. And here, the standards speak about 12,000 byte payloads that should be transmitted every 10 times per second. And the end-to-end latency here is expected to be much higher, much lower at 3 milliseconds. Another type of use case would be remote driving. Here we have a teleoperator that can connect to a car. What is important here is not these smaller payloads that are transmitted or smaller, bigger payloads, but it's basically the throughput. And here, the uplink throughput is expected to be reliably transmitted at around 25 megabits per second, and in downlink 1 megabit per second for this teleoperator to be able to drive a car remotely. And last but not least, here we are talking about extended sensors, so high throughput sensors, HD map sharing between the cars, high quality video between the cars. And here the standards think about use cases that would require 1,000 megabits per second throughput with 99.99% reliability. Oh, what is special in NR sidelink? Well, it's not only a broadcast system. It's the idea that the nodes can make connections between each other. So we have unicast, groupcast, as well as broadcast transmissions. In NR, there is also the possibility to send some HARC feedback. So there is a new channel defined that would allow the nodes in a group or in a one-to-one type of communication to send feedback to each other. This was not possible in the LTE-based V2X. In release 16, 5G V2X also speaks about communication licensed as well as unlicensed bands. Yeah, these would be the main characteristics of 5G and 5G V2X. This is just talking about the same topic. I'm not going to go too much into the details because I would like to talk to you a bit more about how to test cellular V2X and how is Keysight looking at this technology from a test and measurement perspective. So where is the cellular V2X module fitting into the automotive picture? Well, we have in the cars, we have TCU. It's a telematics control unit, which basically creates the connection between the car and the outside world. It connects in the car with other electronic control units via CAN bus or Ethernet, automotive Ethernet, or with an external device via USB, let's say. And then it connects to the outside world, either via cellular communications, 2G, 3G, 4G, 5G, cellular V2X. It has a GNSS receiver Wi-Fi, and Bluetooth. And you can imagine here there is a pretty wide spectrum that needs to be covered. And this is why I said in the beginning that Mike is pretty busy nowadays. When we test TCUs, we need to think about the RF, the 3GPP protocol, and to think about these radio access KPIs. How do we actually achieve those 6,000 bytes 50 times per second with a pretty high reliability? But we also need to think how this fits into the bigger picture. So the TCU would go in a car, and this car can communicate with other cars via Cellular V2X. Of course, the car would also communicate via the radio access network, via Vodafone, Deutsche Telekom, via the mobile operator. It has the way to communicate with edge computing hosts, or through the mobile network operator's core network, it can connect to the automotive OEM backend for maintenance services, or it can simply connect to the internet. And how do we manage to test these solutions, wireless solutions, end to end? Well, in Keysight, we do have a wide portfolio of instruments that help on the product's life cycle, from the development, from R&D through acceptance. As I mentioned, we need to pass certain certifications. Then the products need to be manufactured with high throughput in order to have the products faster on the market, and the products will in the end be deployed, and we maybe need some maintenance services and ways to test quickly and to find out bugs in products that have been already launched on the market. The solution that I wanted to talk to you briefly today for Cellular V2X is mainly covering the R&D part of the product cycle, and here Keysight is offering UXM 5G wireless test platform. It's a tester that emulates a mobile network and can also be used to test Cellular V2X besides 5G, LTE, or even WCDMA. It's a nice one-box tool that helps engineers such as Mike to go through all the layers of the stack, from RF up to IP and application layer, and this is what it makes it a great engineering solution. What are the particularities of testing Cellular V2X? I mentioned that C-V2X deployments are generally based on PC5, on this direct type of communication between the cars. And as you may imagine, congestion can sometimes be a problem. So if we are on a congested highway or somewhere in a city with lots of cars that would have this technology, that would be equipped with this technology, then it is important to know how the end-to-end system works when we have many transmitting nodes. And the solution that we come with would offer software that works together with this UXM 5G. We emulate a node or more nodes that are as if they are transmitting on the same link as the device under test, and these nodes are emulated in the UXM 5G box. Then we also need to have, for the device under test, a way to make it feel as if it is somewhere in the world. So we need to emulate the GNSS signal, and this one is we also have an instrument for that would basically, as I mentioned, make the device under test, the vehicle under test, think that it is somewhere in China or in Japan or in the US. And then we also have a software that helps to create some scenarios in which you add your cars on it, and you say, okay, this is my vehicle under test. It drives in a certain direction, and I want to make sure that the messages it receives them reliably. So to explain a bit more how this software works, it's basically a way you create your scenarios in on a map. You can say here that, for example, the black node is your device under test, which has been placed on the map somewhere in Germany. And then the red node is an emulated node And you can create scenarios which you tell in this environment. You say that my car is driving towards the intersection. It receives the messages from this red node, and probably the red node would need to yield to let our device under test pass, because it's coming from the right hand side, and let's see what happens and how the software works on the car. The scenario execution is done with the UXM 5G instrument, and in the end, once the scenario is run, we have seen the messages that have been exchanged between the device under test and this emulated node. Then we can also analyze the scenario offline and extract the needed KPIs and assess whether the transmission was right, the latency was right, and so on and so forth. And as I mentioned, one key aspect of testing Cellular V2X is also considering congested scenarios. So this emulated node doesn't need to be alone. We can also emulate hundreds of nodes that seem to be around our device under test. And in that case, we see how the algorithms that decide when to transmit on the channel are transmitting, and if they're transmitting right, or if the messages coming from hundreds of nodes are properly decoded and parsed. One important aspect about testing is always interoperability. So, for example, in the US, Omniair is an organization that has taken over the certification process for C-V2X, the certification process for C-V2X products, and they have certain types of tests that cover from layer 1 to the upper layers, and they are testing the devices to be commercialized in the lab in order to make sure that they would be interoperable with each other. So certification is the path to interoperability. And Keysight is since April 15th a certified equipment for it's a qualified test equipment for Cellular V2X. We have been talking about how C-V2X can be tested, but the question is, how does C-V2X fit into the bigger picture when we have information coming from GNSS, coming maybe from other sensors as well? And we need to consider that the car doesn't have an electronic control unit that only takes care of the C-V2X communication, but there are camera, radar, lidar, and so on and so forth. So in Keysight, we have been thinking about an environment that needs to be created around our system under test. So this, you can consider that it's either your entire car or parts of your car. And what happens is that we have a scenario in which we are transmitting some messages over the Cellular V2X link. The system under test knows also from the emulation where it is theoretically in the world, and it receives some messages, let's assume, in which the car needs to, or the ADAS system on the car needs to take a decision. So a message says there is an accident ahead, you are approaching too fast, you need to brake. And what happens is that this V2X message is received, the position is known, and then we can either trigger the brakes or a warning sign in front of the driver, or something can be done with the powertrain in order to make sure that the accident is avoided. And as I mentioned, in this scenario, we can with this platform we can test in the lab much faster. We can have repeatable scenarios and check whether the software, for example, we want to test this decision-making software, and we want to make sure that the messages that are coming on the V2X link are properly parsed and interpreted. And with the autonomous drive emulation platform offered by Keysight, you can create this environment and do the testing in a hardware in the loop hardware in the loop is a standard type of test for automotive, in which parts of the car, let's say, could be maybe emulated, and some parts are the physical devices under test, and we make sure that all the independent pieces are working together when put together. So probably Mike is speechless right now. He has lots of answers, but also still lots of questions. And this is why he should talk to Keysight. And in the final end, what I wanted to tell you is that in order to have car-to-car types of communications, you need to consider that the environment is changing fast, the frequencies on which technologies are deployed are evolving, the standards are evolving. Testing needs to be done from the physical RF link all the way to the application layer. The right KPIs need to be looked into, and yeah, but we do have answers for everything in Keysight, because we are the masters of emulation. And this would be the end of my presentation. And I'm open now to Q&A. So I'm open. Don't be shy. If anybody has questions, I'm.
Hello, from my side, one question regarding this 5G communication, data rate and so on. How is this in the real scenario for the big metropolitan cities where a lot of data will be moving around? So how this reliability or collision or any end-to-end authenticity of this data can be made ensured somehow in the real life? Is there will be 100 or 99% surety for this data, like corruption or something like that, all that we can rely 100% on the data which is sent or received through different cars and infrastructure and so on? So how this can be realized, or currently what stage we are? Yeah.
Yep, thanks a lot. That's a good question. Reliability is always a question that comes up when we talk about automotive applications. What is basically new in 5G is that it comes with a much wider frequency spectrum in which the devices can operate. So generally with 5G, you have it's not only 20 megahertz or 10 megahertz of spectrum that are available. It can be up to 100 or 200 or 400. It's much more flexible. So first of all, reliability can be achieved on the one hand by transmitting with a lot of redundancy, because you have a lot more spectrum. Then 5G also comes with the radio link is more robust from the perspective of the so it is using OFDM, and the standard has been designed not to have a constant subcarrier spacing between the OFDM subcarriers, let's say, when you create an OFDM symbol, and that makes it more flexible to be used in different types of communication environments. So if you are in a city, or if you are in an area where you need communication over large distances or low distances, so the radio part on 5G is much more flexible. How to ensure reliability? Of course, I personally think that going towards ultra high reliable communications, we cannot simply rely on this car-to-car communication. There also needs to be maybe some sort of help coming from the mobile operators. They need to have some towers installed here and there in which they transmit some messages to the cars. They tell them, hey, this channel maybe is very, very busy. Maybe you can move to the other channel, or the reliability comes from having a little bit more help also from other sides. And another question that I think you asked was because you packed a lot of questions in a question, so
no, I mean,
I'm trying.
it's okay. It was just to, because from the safety point of view, if we receive or transmit that, we are sure that the data what is sent or received are reliable and also correct, and there's no distortion or something, or some, something like the noise or something.
Yeah, I got your question. That is basically coming. It is knowing that the data that was transmitting over the air is the right data to some extent, is embedded into the communication, into the communication between the two nodes. So basically, you have some CRC checks, you have some transport blocks that are transmitted over the air. These transport blocks have a CRC, a cyclic redundancy check, appended to them, and there can be some checks done to make sure that the data was not is what it should be. And then, of course, you can think about how reliable the transmission has been over the air. That's one aspect of it. But then maybe you can also think about it from a cybersecurity or security type of from a security perspective. Is this data coming from a reliable source? And there are also mechanisms that are being considered. I'm not covering them in this presentation, and it's not fully my area of expertise, but what I know is that there are some certificates that can be used by the nodes to ensure integrity of the transmitted messages. And the idea would be, for example, that again, the cars would be driving around, and in some geolocation, for example, there is a network operator that transmits the certificates, and these certificates are valid in a certain geographical location for a certain amount of time. And then, like this, you can slowly increase the security and the reliability, let's say the integrity of the transmitting nodes. So yeah, you can think of it integrity and reliability on more levels.
Open topics, especially like cybersecurity. This can be also, but I think this is an advanced development that will be happening, I think, in near future. So
I know that there is a lot of work done actually around C-V2X security, because again, it has to do with cars, of course. So people want their cars to be secure. They don't want to get bogus messages from cars that don't exist, or from some pirate of the highway. So I know that there are a lot of publications and work done in this direction. And as I mentioned, one of the ideas I read about was, for example, this one, that the mobile operator, you still have a connection to the mobile network, and there are some servers from which messages are sent to the cars in certain areas, and they are told, okay, in this geographical location with a certain surface, you should be using as Audi or as BMW or as Daimler or whatever, or Tesla, you can use these certificates. And once you move somewhere else, you need to change them. And the certificates would be also valid for a certain amount of time. So if somebody manages to decode those, would manage to get some messages to spoof, then the information would not be valid for a very long time.
okay, thank you for the clarification. Thanks.
Well, any other questions? In any case, if somebody has extra questions, I can also answer them via email. I'm here in my Keysight office at home, so I'm willing to also answer email to questions over email if you have questions. Otherwise, Florian,
Yeah, if there are no other questions, I think we can conclude here. Thank you very much, Radu, for the presentation and for the interesting details. And thank you everyone for attending the session. We'll publish it on the Keysight Romania channel on YouTube. So in case you are interested, you can revisit it there.
Cool. Thank you very much. Thanks for your time and attention. And stay in touch. Stay safe. Thank you. Bye-bye.
Thank you, Radu. Bye.